A German mathematician named George Cantor developed the theory of the cardinalities of infinity. Let's break this down. First, we need to know cardinalities, which is the number of elements in a set, the size of the set. Next, we need to know what infinity is. Infinity is not a number. It's a concept. Infinity is weird. Let's look at an arrow moving towards a target. There are infinite points between it and the target. And even as the arrow moves forward, there are still infinite points towards the target. No matter how close it gets, there are the same number of points. The arrow never reaches the target. But of course we know that the arrow does move forward and the arrow does meet its target. This is known as Zeno's paradox. Let's look at another paradox called Hilbert's hotel. Hilbert's hotel is like any other hotel, except instead of a finite number of rooms, there's an infinite number of rooms. And they're all full. Let's say a person wants to come in and book a room. How can they do this? Well, simply move everyone up one room until eventually you have the last room remaining that the person can go into. Okay, let's talk about sets. You can say that two sets have the same cardinality if you can compare each element in one set to each element in another set. This is called mapping. Let's say I have this set of shapes and this set of numbers. I compare each of the numbers to each of the shapes. Therefore, the two sets have the same cardinality. Let's look at the set of natural numbers, which goes from 1 to infinity, and the set of even numbers, which goes from 2 to infinity. We can directly compare each of the even numbers to each of the natural numbers. Therefore, they have the same cardinality. There are as many natural numbers as there are even numbers. Let's compare the rational numbers to the natural numbers. We'll put the numerators on one side and the denominators on the other. Now that we have all the rational numbers, we can find an order to put all of them in. You can see that we can compare each of the rational numbers to each of the natural numbers. There are as many natural numbers as there are rational numbers. What we've been looking at is the countability of a set, the ability to map one set to the natural numbers. If you're able to count the set, it's the same size as the natural numbers. Okay, what about the real numbers, which is both the set of rational numbers and the irrational numbers? Let's create a set of real numbers and map them to the natural numbers. Using Cantor's diagonal proof, I can show that there's at least one number that isn't on my list. Take the first digit of the first number, the second digit of the second number, the third digit of the third number, etc. We change each of these numbers and there's a new number that isn't on the list. It can't be the first number because the first digit changed, it can't be the second number because the second digit changed, and it can't be the third number because the third digit changed. No matter how big the list, even infinite, there's at least one number that wasn't on it. Okay, so what does this mean? That means that there's more real numbers than there are rational numbers. Infinity is bigger than infinity. There are different sizes of infinity. So just how many sizes of infinity are there? Are there even infinite infinities? Cantor's paradox explains that there are infinite cardinalities of infinity, and the set that includes all the infinities is the biggest of them all. It is impossible for us as humans to imagine the infiniteness of infinity, but that doesn't mean mathematicians will stop trying to understand it. And I hope now you can understand it just a little bit better. Thanks for watching.